My name is Michael Arntzenius. I'm a PhD student at the University of Birmingham in England. And I'm going to be talking to you about a research language I've been working on called Datafun. Is this working? It's not working. Oh, no. Oh, I know why it's not working. All right, so a bunch of the talks you've probably seen today have gone something like this. Here's this problem we had. Boy, was it a hard problem. Here's a system we built, and it solves this problem really well. This system is so great, in the future, we're all going to use this system. This talk is a little more exploratory than that. Datafun is very early stages work, and there is no single problem that I can point to that it solves better than any existing system. So instead of getting into the details of how it solves some specific problem, I'm going to try and discuss the ideas behind it in the hope that you'll find them as interesting as I do, and maybe be able to take some of these ideas away and use them. So the driving idea here is, what if our programming languages were more like our query languages, and vice versa? So a lot of programs, at its core, a lot of programs are manipulating data, right? Asking questions about it, transforming it, shifting it from place to place. But our general purpose programming languages tend to focus more on the computation side of things than on the data side of things. They often make very simple things quite difficult, like if we want to put our data in memory versus if we want to put it on disk, we have to do totally different things. We have to write totally different pieces of code. And we have to worry about all sorts of representation issues. And for these reasons, databases exist, right? They give you a framework for representing data that's fairly general, very nice. They give you lots of useful ways to operate over it. They solve the issue of, like, do you want it on disk or do you want it in memory? Because they'll keep it on disk and also load it into memory as needed. It's very nice. But you wind up with a layer between yourself and the data, because you're working in this general purpose programming language, and then you have to communicate to this database. And this causes what's called an impedance mismatch, right? So I'm sort of looking at what is the smallest thing we could do to begin to bridge this divide, to begin to heal this divide. Can we find some happy medium that merges what to me is general purpose programming? To me, general purpose programming is functional programming. That's sort of my native language. And database query languages. So this talk is going to look kind of like this. First, I'm going to explain what I mean by a functional query language, because this idea isn't original to me. And it's a very nice idea. And I'm going to explain what I mean by it and what Datafun's take on it is. Then I'm going to talk about Datafun's sort of intellectual forebear, Datalog, and what it's really good at and what features Datafun takes from it. And then if I have time, I'm going to discuss my most current work on Datafun, which is incrementalizing it. That is to say, having it handle small changes to its inputs, or to the state of the database, if you prefer, in a smooth fashion without having to recompute everything from scratch. And this also turns out to interact in an interesting way with section 2, with the feature that we inherit from Datalog. So the normal way of thinking about data, well, one way of thinking about data, the way that SQL teaches us, is your data is arranged in tables, right? And a table has some number of columns, and each row has a value for each of those columns, right? So here we have a table that one might create if you wanted to study the genealogies in the work of J.R.R. Tolkien. There it is. It tells you that Arathorn is the parent of Aragorn, Drogo is the parent of Frodo, and Galadriel's parents are Eowyn and Finarfin. And on the right is a query that you might use. In this case, it tells you who the parents of Galadriel are. Right, so it will return Eowyn and Finarfin. Right. So this kind of approach dates back to an idea generated in the 70s, like so many computer science ideas, called relational algebra. And that name is kind of a doozy. What do relations and algebra have to do with tables and queries? Well, the relation part of it is what I'll explain first. A relation is a mathematical name for a set of tuples, right? And we can see a table as a set of tuples. Every row becomes a tuple in the set. And the columns are just, which field, which part of the tuple do you want to get at. So, our table can be looked at as a set. So this amounts to nothing more than changing the way we look at our data. But once we've looked at our data this way, a certain question becomes natural when we look at it from a functional point of view. Tuples and sets to a functional programmer are just data types. We have lots of data types: lists, dictionaries or maps, hash tables, trees, anything you like. So, and we certainly have tuples, so why not sets? Why not just add sets to our language, right? And some languages already have, set data types in them. And then another question presents itself, which is, if tables are just sets, what are queries? And the answer to this question is the core idea behind functional query languages, which is, you may have heard of this, you may have used list comprehensions if you've programmed in Python or in Haskell. And they're a very nice syntax for manipulating lists, for iterating over them, filtering them, applying functions to each element, combining lists. Well, if we can have list comprehensions, why not set comprehensions, right? And it's exactly the same idea, except instead of iterating over lists, we're iterating over sets, and instead of producing a list, we're producing a set, right? So suddenly order and duplicates don't matter. And my assertion is, anything that you do with a query in SQL, you can do with a set comprehension. Right? And set comprehensions provide a very nice and natural way to express queries. So here's that query we saw before, finding the parents of Galadriel, and here's how you would write it. And this is valid Datafun code. This is how you would write it in Datafun. Right? So find me every parent, where parent comma child is in our parent-child table, parentage, right? And the child is Galadriel, right? So to give another example to show that you can do some more non-trivial things, let's consider trying to find siblings. So here's the SQL for finding siblings, and it's a bit noisy to me, but it says, let's find two distinct children, right, who have the same parent, right? We join our parentage table on itself, find two rows in it which share a parent but have distinct children. Great. And below is how you would write that as a set comprehension, right? So find me, parent comma A, find me an element parent comma A in our parentage set. Find me an element parent comma B where that parent is the same as the previous parent, which is what that exclamation mark means. It's just a syntax sugar for an equality test. And make sure that A isn't equal to B, because we don't want to say that a person is their own sibling. So this is almost all there is to say about the idea of functional query languages, without getting into all sorts of implementation details in their history and so forth. So here's our recipe, basically, for a functional query language. Take a functional language. Take your favorite functional language. Add sets as a data structure, and add set comprehensions as a way of manipulating those data structures. Are we done? Can I finish this talk? Well, there's a burning question that I haven't answered. Can we make it go fast? Can this actually do the things we want it to do in a reasonable amount of time? And I believe it can, but we have to impose some limitations. So I can't convince you that every single optimization in the database literature carries over to this way of doing things. So I'm only going to give you one example, because there's a vast literature on optimizing databases. And that example is sort of the simplest, smallest database optimization, join reordering, or in a functional language, loop reordering. Are these two set comprehensions equal, right? Am I allowed to see one of them, say, nah, that won't run fast enough, and turn it into the other? Not in general. There are two things that will keep me from doing it: side effects and non-termination. So side effects, the first, these are just looping over two different sets, expr1 and expr2, which are just standing for arbitrary expressions, right? So if I put a side effect into my loop, right, like printing a value, depending on which order I loop over things, I will print things in a different order. That's different behavior. And that means I can't replace one of these expressions by the other. I can't decide to optimize one into the other. All right, so that's pretty straightforward. Does that seem to make sense to everybody? Okay. The other one is a little more tricky, which is non-termination. So let's suppose one of the expressions for a set I'm looping over is the empty set, right? Which I'm representing here as curly braces, closed curly braces, right? And let's suppose the other expression I'm looping over doesn't terminate. It infinite loops, right? So I've represented that here with literally infinite loop. Well, if I run it the top way, where I'm looping over an empty set first, well, looping over the empty set, there's nothing in it, so you're done immediately. There's nothing, there are no results to your set comprehension. There's nothing further to do. You get the empty set back. On the other hand, if I loop over the expression which fails to terminate first, I'll sit there waiting for it to terminate, and it won't. And I will never give you back your set that you wanted to get back. So non-termination also prevents us from making this optimization. So what's my solution? Ban them. No side effects, no non-termination. Pure and total functional programming is what I want to do. So purity is fairly uncommon, but there's at least one language that some people here will have hopefully heard of, Haskell, that is pure, at least by default. Totality, that is to say, banning non-termination, all programs must terminate, is less popular. But you're beginning to see some examples of trying to make more or less general purpose languages that have totality as a feature. Idris, for example, can handle both total and non-total things. So it's an open question how expressive a total language can be. But I think for query language purposes, it's probably fine. So we take a pure and total functional language, we add sets and set comprehensions, and then we optimize. And of course, this is the bit that's kind of an open question. How much can we optimize? Can we get all of those things that we had for databases and apply them to sets and set comprehensions in a pure and total language? And I think we can, most of them. So what have we gained from this approach if it works? Well, we're in a functional language. We can use functions and higher order functions. We can factor out repeated patterns. We can do all those things that we're used to doing, right? We have brought functional programming and database programming a little closer together, taken baby steps towards healing the impedance mismatch. Also, sets are now just ordinary values. You can do anything that you want to do with them. They're not these special table things that have to be manipulated with this one part of your language and that are different from numbers or strings. You can stick them in a closure. You can pass them to another function. You can nest them inside of another set if you feel like it. And typically in databases kind of have to make this global choice about their semantics. Do they care about duplicates or not? Right? SQL sometimes can care about duplicates. Relational algebra, the idea invented in the 70s that it was based on, kind of said no duplicates. Right? You shouldn't care about duplicates. And there are holy wars about this. There's something called the Third Manifesto that complains about how SQL isn't really relational. Anyway, my solution is just like, have them all, right? Use types to distinguish. If you don't care about duplicates, if you want to say there are no duplicates, then you have a set. If you do care about duplicates, you have something called a multiset or a bag. And if you care about duplicates and also about order, you have a list. So you just use your type to say which semantics you want. Okay, but nothing comes for free. What is the cost of all this? And the cost is that we've just tried to reinvent the world. And now we have to implement all that stuff. And we have to implement all the stuff that makes functional languages hard to implement and all the stuff that makes databases hard to implement at the same time and figure out how they all interact. And that's hard. So this is one of the reasons why Datafun is very early stage work. And we're going to focus probably not on beating databases at their own game. So yeah. There's a lot of stuff to implement. All right, so that's basically the first part of my talk. Now I'm going to talk, and again, basically none of this, apart from requiring totality, is particularly new to Datafun. Other people have had the idea of functional query languages before. Now I'm going to talk about what really is new to Datafun. And so I'm going to talk about this by introducing a particular problem and solving it with another language called Datalog. So the problem is this. We have our data from before, our genealogies, our Tolkien genealogies, and we want to answer this really important question. Is Eärendil one of Aragorn's ancestors? Relational algebra, the idea from the 70s on which SQL was based, cannot answer this question. It cannot do it. Doesn't matter how clever you are, it literally cannot solve this question. Because it essentially involves a sort of unbounded search. It's technically bounded, but you don't really know the bound in advance. You're asking, is Eärendil a parent, or a grandparent, or a great-grandparent, or a great-great-grandparent, or a great-great-great-grandparent? Any number of greats. I don't care how many greats I have to put in. Is Eärendil that many great-grandparents of Aragorn? And for any fixed number, relational algebra can do it. But for an arbitrary number, it can't. SQL technically can, but only because of an extension. Admittedly, it was standardized in the 1990s, so it's not particularly new. But most importantly, it does not fit on a slide. So I'm not going to explain the SQL extension that solves this problem. Because instead, I'm going to explain Datalog, because Datalog solves this problem in 2 lines of code that are extremely beautiful. So Datalog, this isn't Datalog yet. Datalog comes from the line of logic programming, which was this idea that, hold on, why are we programming at all? Why are we telling the computer what to do? Why don't we just tell the computer what it is we want? Why don't we just specify the problem and have the computer figure out how to solve it? It's a beautiful, lovely idea. Implementing it is hard. Datalog is a restriction of this idea to the cases where you can implement it pretty well. Right? It's like, let's scale down our ambitions. Let's not try to solve every problem by specifying it. Let's solve the ones that we know how to solve just from their specifications. So here's a specification for the question of when somebody is somebody else's ancestor. X is Z's ancestor if X is Z's parent, right? If you're a parent of someone, you're their ancestor. And also, if you're a parent of one of their ancestors, you are one of their ancestors, right? That's the second line, right? So this defines what it is to be someone's ancestor. But this is English, and English is hard for computers to parse. So let's try and make this look a little more like logic. It's called logic programming because it's based on formal logic. So let's replace our English possessives by something a little easier to parse, right? We'll put a predicate and then some arguments. So in this case, the predicates we're concerned with are ancestor, which tells us that somebody is somebody's ancestor, and parent, which tells us that somebody is somebody's parent. And just for kicks, let's make it look a little more computery. Let's replace the if by a colon dash and the and by a comma. There's really, you don't have to do that, but they did. It's just what the syntax of Datalog looks like. And this is valid Datalog, and it solves the problem we set out to solve. We took 2 steps from an English specification of the problem, and we arrived at a runnable computer program that solves the problem. This is what's so lovely about logic programming. Okay. How do we make Datafun solve this problem? The idea behind Datalog is that it's deductive. You give it a set of rules, like those if-then rules we just provided, and it chases them to their logical conclusion. It's not clear, and at least not immediately clear, how to capture this feature in a functional language. So let's try running a Datalog program and see what it's doing, and then see if we can capture that. So this is how you run. This is the naive conceptual version of how you run a Datalog program. All right, actual implementations do smarter things. Okay, so we're going to repeatedly apply the procedure at the top. We're going to pick a rule, find some facts that satisfy its premises, which are the things on the right-hand side of the colon dash, which stands for if, right? And then, if we can find some things satisfying its premises, we're going to add the conclusion to the set of facts that we know. And we're going to start with just two facts, right, that tell us that Idril is the parent of Earendel, and Earendel is the parent of Elros. So before we start, what should the result look like at the end? What are all the ancestry relationships here? Well, Idril is an ancestor of Earendel, clearly, and Earendel is an ancestor of Elros. That's just because they're parents. And there's a grandparenthood relationship here. Idril is the grandparent of Elros, so we should also have that Idril is an ancestor of Elros. So that's what we should figure out. So now let's try it. I'm going to pick a rule. First rule, why not? I need to pick a fact satisfying its premise. First fact. Great. So here X is Idril, Z is Earendel. So now we take the conclusion and shove it into the facts that we know. All right, so now we know that Idril is the ancestor of Earendel. Now we're going to do the same thing, faster. Right? So we know that Earendel is the parent of Elros, and we have a rule telling us that therefore Earendel is Elros' ancestor. Great. Okay, now let's try the second rule for a change. Okay, can we satisfy its premises? Well, we need that X is a parent of Y, while Idril is a parent of Earendel. And now we need to find someone who Earendel is an ancestor of. We look down our list, and the first ancestor fact doesn't match because it's about Idril being the parent of Earendel, not Earendel being someone's parent. But the second one does. And so now X is Earendel, Y is Elros, and X is Idril, Y is Earendel, Z is Elros. And we add the conclusion to our set of facts. And now we are done. Why are we done? Anybody? Yeah.
Because if you reapply the process, you'll just rederive results that already exist.
Exactly, right? So we said if you reapply the process, you'll just find results that already exist. No matter which rule we pick, and no matter which facts we pick satisfying its premises, we're going to derive a fact that we already know. And this is not immediately obvious from looking at this, but a computer can check it. It's not too hard. And so we're done because nothing is changing anymore, right? So what we just did was we repeatedly applied a set of rules until nothing was changing anymore. How could we capture this in a functional way? I heard the word fixed point, which is great, but you're jumping a little bit ahead. Instead of a set of rules, let's use a function. This is functional programming after all. A function is kind of like a set of rules, or more like a single rule. So we'll see whether this works. It's just a hypothesis. And what do we mean by nothing is changing? Well, we're repeatedly applying a function. So we're repeatedly applying it until the output that we get at some point is equal to the input that we just applied it to. And the name for this is a fixed point, right? Because it's a point of value x such that f of x equals x. It's fixed. If we keep applying the function, we're not going to get anywhere new. And this is what Datafun does. And this is the Datafun syntax for finding one of these things. You say fix x equals, and then you write an expression in terms of x, and it will treat that expression as a function of x, and repeatedly apply it, starting from the empty set. Start out knowing nothing, why not? It's a good place to start as any, until you reach a fixed point. So here is the translation into Datafun of our running example. Right? So it's not immediately obvious what's going on here, but let's split this into parts. The first part, so this is a union of two things, right? That's what U means, union two sets. The first part corresponds more or less to the first rule. It says if some tuple or pair is in the parent set, then it's also in the ancestor set, right? If x is a parent of y, then they're an ancestor of y. The second part is the interesting one, right? It's one where we need to bust out the set comprehensions, right? And it's looking for a pair x, y in parent, and a pair y, z in ancestor, where those two y's are equal, right? So just show of hands, how many people think it's clear that the thing on the bottom calculates the same as the thing on the top? Okay, some hands, but not enough. So we're going to run it and show that it calculates the same thing. right? So here's the function that we want to apply. I've just taken ancestor and replaced it with big X, right? Here's the definition of parent that we're using, right? Those are the parentage relations we're starting with. And we're going to start with the empty set. That's what circle with the slash through it means, empty set. So, all right, we substitute empty set into our function as big X. We get this expression. Okay, what does this expression evaluate to? Well, I can use a trick, because the right-hand set comprehension is looping over an empty set. It's going for every y, z in empty set, and there ain't nothing in the empty set, so that whole thing produces nothing. It's empty. So this just turns into parent. This is just parent. Okay, all right, first iteration done. Let's apply our function again. So now, let's look at this for a while. What is this doing? It's taking parent, union, this thing that looks for pairs in parent that have a common middle thing, where one of them's child is the same as the other one's parent. So this is, in other words, calculating grandparents. This is parent, union, grandparent. And if we actually calculate that out, this is the set you get. And this is exactly the set of things that we knew if we go back to our Datalog example at the end. These were the ancestors. Right? And this happens to be a fixed point of this function. If you run it again, nothing will change. Right. So I hope I've convinced you that, oops. I hope I've convinced you that fixed points are as expressive as Datalog's ability to define predicates recursively by rules which reference themselves, such as the rule for ancestor. But can it go fast, right? And this is the part where I admit that I don't know. But I have reason for hope. And that reason for hope is that we've just, as of about 3 weeks ago, figured out how to apply one of the optimizations that's standard in the Datalog literature to Datafun. And we've found out that it's equivalent to another thing as well. So in the third part, I'm going to talk about incrementalizing Datafun. How am I doing on time? How many minutes do we have? 50. OK, yeah, 12 minutes. Sure. So here are 3 problems that at first seem separate. View maintenance. You have a database. This database is changing. It's changing all the time. People are sending updates to it. But you also have a cached query, something that's called a view in a database, right? You tell your database, here's a query. Please maintain the results of this query for me so that I can very quickly ask for its results again. It's not quite a cache, but it's close enough, right? And we want to keep this view up to date even as the database is changing behind us. But we don't want to have to re-execute the query from scratch every time, because that will be slow. So how do we do this? I'm not going to tell you. I don't have time. But here's another problem. So Datalog can be thought of as a deductive system. Repeatedly apply rules, repeatedly deduce things. But in that example that I showed you of running Datalog, I sort of magically picked the rules that I knew would result in something interesting. It's not clear how to do that in general. How do you avoid picking a rule that's going to generate a result you already know about, right? And finally, incremental computation, which is this idea from functional programming languages and from programming languages research in general. You have a function defined in some language, and its inputs change by a little bit. You want to rerun the function to compute the updated output, but you don't want to rerun it from scratch, because that would be slow. And I assert that all of these 3 things, well, the previous 2 things are just special cases of the third thing, right? So with view maintenance, that's not too hard to accept, right? A view, a query, is just a function of the state of the database. And when the inputs to that function change, i.e. the database updates, you want to figure out how the output, i.e. the cached query, changes without recomputing it from scratch. It's a little less obvious how Datalog's recursive queries, how trying to avoid applying rules that generate boring facts, things you already knew, is related to this. So there's a paper that describes a solution to problem 3 that is the paper that we've based our work on Datafun in that solves problem 3 and problem 2, except for Datafun rather than Datalog. It has a rather intimidatingly long title, A Theory of Changes for Higher Order Languages, Incrementing Lambda Calculi by Static Differentiation. And the way it works is like this. Every type gets an associated type representing changes to that type, right? So how that thing might be updated. So for example, natural numbers, right? Numbers 0, 1, 2, 3, 4, 5, 6, their type of changes is going to be the integers, because they might increase or decrease, right? If I turn 3 into 2, the change that does that is -1, right? If I have a type of pairs in my language, then a change to a type of pairs is going to be a pair of changes, the change to the first part of the pair and the change to the second part of the pair. And you go through every type in your language and figure out what the type of changes for a given type should be. Every type also gets a little operator that adds a value and a change and gives you the updated value. It's that simple, right? So for natural numbers with integers that change things, you're literally just adding them, right? For pairs, you're just pairwise updating each part of the pair. And here's the interesting part. A function gets a derivative. So this isn't quite the notion of derivative from calculus, but it's somewhat similar because it tells you how your function changes. If f takes things of type A to things of type B, the derivative takes a value of type a change to it of type delta A, and produces the change in the output, right? So to sort of explain how this is different from regular calculus, let's say our function is f of x equals x squared. Square is the value. The derivative then is going to take the value x and a change to it, dx, and this is the result it's going to give, right? Why? Why is that the correct derivative, right? Because that isn't what you would call the calculus derivative. The calculus derivative of x squared is 2x, right? So why all this extra junk? Well, because we care about computing exact changes, not just the local approximation, right? And if we add the function and the function that computes the change, right, we get this expression, x squared plus 2x dx plus dx squared. And if we manipulate that a bit with algebra, we get x plus dx squared, which is just the original function applied at the updated input, right? So the derivative lets you compute what the new value of your function will be. So right, we have, as of 3 weeks ago, figured out how to extend this technique to apply to all of Datafun. So all expressions get a derivative that tells you how they change as their inputs change. The only implementation of this, unfortunately, is in my notebooks and in a GitHub repo. But not code yet. We're working on it. So how does this help us find fixed points faster? Right? Because I promised you this would help us find fixed points faster, help us solve Datalog queries faster, which turn out to be just fixed points. So the normal way to find a fixed point looks like this. You start with the empty set. You apply your function. You apply your function again. You apply your function again. You keep doing it until you hit a fixed point. It's very straightforward. But the neighbors in the iteration pattern, you know, are going to overlap a lot. They're going to share a lot of information, and generally computing the next step from the previous step ends up recomputing a lot of things, and we'd like to avoid that. So what if we could only compute what was changing between iterations? And now, maybe, we begin to see how derivatives could help us because they help us compute what changes, and only what changes, not the whole thing. So, these are the equations that we use to figure out the fixed point of a derivative faster using the fixed point of a function faster using the derivative of that function. So the idea is that we're going to have a sequence, you know, x0, x1, x2, x3, that is going to be the same as the sequence of iterations of the function that we had earlier, empty set, f of empty set, f of empty set, and so forth. But we're also going to have a sequence of derivatives that is going to help us find it faster. So the initial value of x is empty set. That's where we start. The initial change is f of empty set, because that's the next value. And we're representing changes to sets as just the set of things we add to them, right? So the kickoff, the thing we start with, the change that we start with is going from empty set to f of empty set. And then to calculate the next actual value, the next x, we take the union of the previous x and the change to it, right? That's how we apply a change, we just union. And then the part where we use the actual derivative is the next change value, the next value of dx, is going to be the derivative applied to the previous actual value and the previous change, right? And it's very simple, and it works. Whether it makes things go really fast, we're not sure yet, because we haven't implemented it. But we hope. So, takeaways from this talk. Set comprehensions are a really powerful query language. They let you do everything you might want to do in SQL. Fixed points let you do recursive queries, like you can do in Datalog, which can help for solving certain sorts of problems. And incremental computation, which is this very general idea that's useful in its own right, also helps you find fixed points faster. And we think generalizes one of the standard optimizations in the Datalog literature called seminaive evaluation, which I didn't talk about because, well, I think it's just that faster fixed point. Datafun has all three of these things, or soon will. So that's my talk. And I think I have some time for questions if people want to ask questions. Yeah?
Yeah, in the motivating example for using a single language, I'm wondering why that instead of laziness. Does laziness solve that problem? Would it solve all those classic problems?
I don't think so. So laziness, representing, right, so the question is, in the motivating example for why use a total language, why not just use a lazy language? Would that solve the problems that we're trying to solve? And the answer is I don't think so. Because even in lazy languages, you can write expressions that don't terminate at all. You just ask for their value, and they just like, nope. Right? In Haskell, you can do this with let x equals x. Right? It's really easy. Right? Anything you do with x is just going to hang. Right? So the optimization that we'd like to do, loop reordering, is still invalid, even if your language is lazy. And laziness adds all sorts of difficult problems, like how do you represent sets lazily and also efficiently? And at least as far as I know, it doesn't interact nicely with this iterative fixed point approach. Because this iterative building up fixed points from empty set is kind of, feels very eager to me. I could be wrong about that one, so I'd be interested if anybody has other opinions. So, yeah?
I'm not sure about this. Did expert systems in the past and Prolog have this similar issues as well?
I don't know. So Prolog, so the question was expert systems in the past, which were built on Prolog, presumably had similar problems and maybe had some way of solving them. And my answer is I don't really know whether they did. I don't know all that much about Prolog work. I know Prolog itself is Turing complete, so you can have non-terminating things in Prolog. But just like you can have non-terminating things in Haskell, but you still do useful things in Haskell, you can still do useful things in Prolog. So for us, non-termination is important primarily because we want to optimize things. I don't know whether Prolog makes optimizations on the assumption of non-termination or not. Yeah.
This is a really quick one. What was the type of the derivative of the function there? It was a to alpha to delta a, was it b or delta b?
Right, it takes an A and a change to A and produces the change to B, the change in the output. Yeah, okay, and yeah.
One of the challenges that people have run into trying to embed relational algebra in functional languages is around by aggregation, which aren't quite full. Have you thought about that issue with
Yeah, so the question was some of the problems that people have run into in trying to embed relational algebra-like stuff into functional languages is things like group by and other forms of aggregation, which aren't exactly folds. Was that? Yeah, okay. Yeah, so aggregation is an important thing, and we hope to add it to Datafun, but we haven't done it yet. We have some ideas. We think that just as sets and set comprehensions are related to semi-lattices, bags and bag comprehensions and aggregations that work over bags are related to commutative monoids. So an example of an aggregation that is a commutative monoid would be adding things. That addition is commutative, it's associative, and it has an identity element 0. That is what I mean by a commutative monoid, right? So you have something that does nothing, the identity 0, it's commutative, and it's associative, right? Reductions over lists, similarly, you just need associativity and identity. So we think that there is a relation between various ideas in abstract algebra and how aggregations work, but we haven't fully chased those up. There have been some people who've chased this idea. There's some paper by Boudieu and Plotkin whose title I forget. It's something like multilinear programming for big data. So yeah, we have some ideas, but do not have a solution for that problem. Yeah?
There's a talk here a couple years ago on something called Bloom. Bloom that like relates to a lot of the same concepts. You know, is there? I think it was also the person making came out of I think working on Datalog. I don't know. I was just wondering what the relationship there is, or if there's.
Sure. So the question was sort of, is there a relationship between this system and Bloom, which was the system that talked about at Strange Loop a few years ago? Not directly. I was kind of indirectly inspired by Bloom to start thinking about these kinds of problems. Bloom is a tool for tackling distributed systems problems, whereas this is just a query language and we have no idea how to distribute things on it or how to tackle the same kinds of problems. But there are definitely similar ideas going around, and certainly both Bloom and Datafun owe a lot to Datalog, right? So Datalog, I think, is getting a bit of renewed attention at the moment, which is well-deserved. It's a really cool language and a really cool idea. So no direct relation, but definitely some shared inspiration. I think maybe if there are more talks, we should take them offline. So thank you.